question.
Yeah.
We get our homework. We have our homework assignment by tomorrow afternoon.
These by tomorrow afternoon?
Mainly the one.
That doesn't seem likely. I think the grader's pretty fast, but I can't imagine him getting it done before Monday.
Give us some.
The 16.9? How about I post it on my door, like in the glass by my door? I don't want to send it out electronically because those get handed down more easily from generation to generation. But if I just put it up, then you can look at it and nod your head and not take a picture.
I was thinking more about the standard set method. If we can't get those back in time, could you?
Oh, well, you mean the assignment that you submitted last time?
Yes.
Oh, yeah, I bet you'll get that back soon.
You think we can get a solution for the last two problems today?
Okay. So we're going to talk about channel design today, and actually we're going to start with that BOD problem that we had to leave off with last time. Remember, we were talking about hydrogen sulfide, and the problem with pipes when they are carrying a very low flow rate is that the water is moving slowly. It doesn't aerate very much. You know, when it's just sort of stagnant and not moving quickly, then oxygen doesn't get transferred into the wastewater, and the waste that is in the wastewater breaks down the oxygen, uses it up, and then the waste products, that the sulfur in particular, are consumed anaerobically. And so hydrogen sulfide is what happens when there's sulfur dissolved in the water and it gets used up anaerobically. It's a poisonous gas where concentrations as low as 300 ppm are fatal. And the especially scary thing about it is that at first you'll smell it, but then it desensitizes your smell, and so that you don't have the capacity to smell it after the first few minutes. And so you'll think maybe, oh, I smelled something, but now it's gone, when really it's not gone. It's just that you can't smell it anymore, and you're about to succumb to hydrogen sulfide poisoning. People who work in enclosed spaces often have to carry with them little monitors that will alert them against hydrogen sulfide, but from the hydraulic design standpoint, what we want to do is ensure the minimum velocities to help prevent BOD, which is the waste that is in wastewater, from being converted into hydrogen sulfide. And this is an empirical equation that just allows you to estimate how much BOD potential there might be, how much potential for generating hydrogen sulfide based on the concentration of waste in the water, and then some of the hydraulic parameters like the flow rate, the slope of the channel, and then the wetted perimeter to the top width. And according to this empirical model, that if you calculate a Z value less than 5,000, then probably hydrogen sulfide won't be formed. 10,000, it probably will be formed, and then there's this middle ground where it's possible, and you just have to sort of be looking out for it. So here's an example that just works through the both partially full sewer, and also the impact of having the BOD, which is the wastewater constituent in there. We'll go through this one quickly so we can save most of the time for the channel design. But here in this example, we have a pipe diameter of 750 millimeters. And the water has a temperature of 33 degrees Celsius. And we care about that for more than just the fluid properties. We actually care about the temperature of the wastewater, because the warmer the water is, the more easily bacteria break down BOD and sulfur into hydrogen sulfide. So the temperature is 33 degrees Celsius, and we'll use that in calculating the effective BOD. The slope, we're told, is 0.8%, so 0.8%. And the N value is 0.013. This is a concrete pipe with an N value of 0.013. And the slope, 0.008. 0.8 divided by 100. Now, our equation for a partially full pipe says it's theta to the negative 2/3 power times theta minus the sine of theta to the 5/3 power, 20.16 times n, q, diameter to the negative 8/3, slope to the negative 1/2 power is equal to 0. And finally, we know the flow rate that has to be carried is 0.92 cubic meters per second. Okay, so we put all of the knowns into here, and we can solve that theta is 4.23 radians. You can either do that using Excel, where you're using a guess value of theta and you're playing around with theta until you get the left-hand side of the equation equal to 0. Some equation solving calculators can solve for it directly when you put in the known diameter of the pipe, the known flow rate, known n value. Anyways, this is our theta, which is telling us it's more than half full. Because if it was 3.14 radians, that would mean it's half full. So in this case, here's the water surface, and the angle is 4.23 radians. So that's talking about this angle there. Okay? So the wetted perimeter is d times theta divided by 2. Giving us a perimeter of 1.586 meters. So that's talking about the wetted perimeter, this length here, where the water is in contact with the outside of the pipe wall. The top width b is d times sine of theta divided by 2. So it's 0.75 meters times the sine of 4.23 divided by 2. We get that the top width is 0.642 meters. And that top width distance is just this, where the water surface is open to the air above it. If that was greater than the pipe diameter, we'd know we're in trouble. It should be less than. The maximum would be equal to the pipe diameter itself. Now, the depth of the water we can solve for using the formula here. The y is d divided by 2 times 1 minus the cosine of theta divided by 2. So 0.75 meters divided by 2, 1 minus the cosine of 4.23 radians divided by 2. And we get that the depth is 0.569 meters. And so that is talking about the depth of water from the bottom of the channel up to the water surface, 0.569 meters. Okay, so we need all those parameters for estimating the effective BOD later on. Well, not the effective BOD, but the Z potential. The effective BOD looks at the concentration of the waste combined with the temperature, because the warmer it is, the more active bacteria will be. And the formula we have is that the effective BOD is equal to BOD to the times 1.07 T minus 20. BOD, by the way, stands for biochemical oxygen demand, and you'll learn all about that next semester when you take water and wastewater treatment. But it's just a measure of how much food for bacteria is in a wastewater, because bacteria actually break down dissolved organic material, and in the process of breaking that down, they require oxygen as well. And so we measure the strength of the wastewater by how much oxygen the bacteria consume as they break down the waste in the wastewater. So in this example, we're told that the BOD, or the strength of the waste, is 350 milligrams per liter. And if we take into account the fact that it's relatively warm, to the power of 33 minus 20, so in other words, 1.07 to the 13th power times 350, that is equal to 843 milligrams per liter. So what that means is if you had 843 milligrams per liter, if this was the BOD at 20 degrees Celsius, that would be equivalent to what we've got, the 350, at the temperature of 33. They both have the same effect on how active the bacteria are. So in our case, we have a relatively low strength waste, but it's very warm. So that boosts up the effective BOD. So now finally, we can calculate this Z factor by the empirical equation. And you'll notice that the slope of the channel is in the denominator. It's in the denominator because the steeper the channel is, the lower the Z value will be. And that means that you want it to be steep. A steep channel is good because it helps the water to get more aerated and it's less likely to go anaerobic. And so there's going to be less risk of sulfide being formed when you've got a steep channel. It's the slow-moving water that's kind of swampy and stagnant that can cause a risk. And in this case, the Z factor is 7373, so H2S may form, is all we can say. It's in that sort of danger zone. It's not guaranteed to be there, but if you wanted to avoid this forming, because not only is it poisonous, we talked about how it's risky to human health, but it's also corrosive. This is hydrogen sulfide. When it gets into water, it will form sulfuric acid. And so the sulfuric acid can corrode any metal that might be in the pipe. Sometimes these pipes are made out of metal, and so then they corrode quickly. But even if it's a concrete pipe, it can cause corrosion issues because concrete pipe is sometimes reinforced, or it can just erode the concrete itself, dissolve it. So hydrogen sulfide may form. So if we wanted to prevent that, we can either increase the flow rate, and that would bring down the Z factor, increase the slope, decrease the strength of the waste, either by trying to restrict the BOD or wishing it wasn't so hot. You can't really control that. You're not going to chill the wastewater as it goes into the sewer. But that just gives you an idea of something that you may potentially notice as you go through the equation packet for the FE exam. They talk a little bit about BOD and hydrogen sulfide formation. So, any questions about this example that we worked? All right, well, let's talk about channel design and not probability and risk. I actually took out the probability and risk part of this semester and I put it into hydrology. So in channel design, we'll mostly be, as engineers, sizing lined channels. Here's a concrete lined channel. You can see it's trapezoidal. This one happens to be meandering in shape. And there's a nice grassy right-of-way on either side of the channel. Those are often put there so that someone could drive along the channel and inspect it, trying to look for any cracks in the concrete or looking for the growth of weeds, because if weeds grow, then they can reduce the hydraulic capacity. So inspection is an important thing, but trying to optimize the capacity of that channel is a big part of what a hydraulic designer would do. You're trying to balance how expensive it is to excavate, because excavating material and hauling it away is going to cost money. But if you don't go down, then you have to make the channel wider. And of course, you'll notice that this has neighbors in the backyard here. You have to buy land if you make the channel very wide. And so engineering is always about optimizing and balancing costs. And that comes into play with open channel design as well. Here's an unlined channel. This looks like it's just sort of a ditch in someone's backyard that's formed. It's going to have a much higher end value because of the irregularity of the channel and also because of the grass that's growing in there. Here's a channel that is lined with rocks to try and prevent scour and erosion. This is actually the outfall of a culvert, and it goes around this bend and then enters a grass-lined channel around that way. And then here they're doing construction on what ultimately will become a plastic-lined channel. This is going to have compacted clay, and then they put down what's called a geomembrane, or a thick layer of plastic to try and prevent water from being lost. But in constructed channel design, we're trying to consider the slope that's available. You're moving water over the surface from one place to another. Probably the one factor that affects the capacity of the channel more than anything else is how steep it is. And you can't really make the channel any steeper than the slope of the ground. You can make it less steep by meandering back and forth. You can't make it any steeper, otherwise your channel starts to go down underground. You're trying to balance the effect of the channel geometry on the velocities that can be seen. And velocity is important in the case of hydraulic design of an open channel, because if you have it too fast, then it will scour the bed. And sometimes these are made out of clay and earth, and you want to avoid the scour of the bed. But if it's too low, then sediment may drop out of the flow and start to line the bottom of the channel, or weeds can form. There are some cases where you actually want water to infiltrate into the soil because water is considered a waste. Like this channel here is probably just receiving stormwater runoff. And so here you'd love it if water seeps down underground, because then that means less water that's going to make its way into the stream. But in other cases, like in Arizona, where they have a 100+ mile channel that takes water from the mountains into Phoenix, infiltration is really a big problem. They don't want water seeping from their channel. They want as much of it to be conveyed to the city as possible. So we'll step through some of these considerations. And in open channels, we can have lined, unlined, and grass-lined channels. By lined, we usually mean with concrete, or sometimes paved with asphalt. For erodible channels, most common, what we're working with is a clay, a compacted clay, and a grass-lined channel is kind of in between. It provides some resistance against scour, but ultimately not as much as a lined channel would. We've already talked about the sections that are the most hydraulically effective, those that can maximize the amount of water that flows through them while minimizing flow area. Because by minimizing flow area, you're reducing the amount that has to be excavated and hauled away, and you're also reducing the amount of liner that has to be installed. And so if you want to calculate flow area, this is Manning's equation rearranged to solve for flow area. The things that you can do to reduce the flow area is to have a big slope or a small flow rate, a small n value. Those are some of the parameters that we have directly under our control. How to minimize the flow area and therefore minimize the cost. Yep, that's Florida. Yeah. They've got a lot of really long, straight canals down there to help drain swamps and increase the availability to develop land. 26 miles, yeah, that's long. I bet it was hot too, right? Oh, okay. Well, I don't feel so bad for you then. The best trapezoidal channel is one that has basically it's a half hexagon. The main reason I point this out, this figure, is to introduce the term freeboard. And when you're designing a channel, you not only want to provide enough capacity just so that the water line, you wouldn't necessarily want the water line right up to the very edge. Freeboard is provided in case if you're going around the bend, actually the water surface curves around the bend. There's something called superelevation, and if you had a tight radius curve, like this is our cross section, a trapezoidal cross section, and the water is going around a bend like this, then the surface may actually be tilted like that as it goes around a bend. And if the velocities are high, obviously it's going to be more pronounced than if the velocities are low. But one of the reasons why you put a little extra height above where you expect the water surface to be is for super elevation around a curve. It may be because of splashing. It could be that there's going to be a hydraulic jump in the channel and there's going to be a lot of vigorous mixing, and so freeboard considerations take that into account. And there happens to be on the equation sheet one of the unfamiliar equations that you don't really need to know, because you're not going to get an equation on the, you're not going to get a problem on the exam having to do with freeboard, but I did notice that a freeboard equation was on here somewhere, unless I'm mistaken. I might have taken it off now that I think about it. Too many? Just cross out the ones you don't think you're going to use. Yeah. So freeboard varies based on the quantity of water you expect to carry, and also the width of the channel is going to affect the super elevation. But here are some of the geometric parameters for what's considered the best geometry, best in terms of minimizing the flow area, A, based on a certain depth, Y. Now, there's a couple of different slopes. We talk about the side slopes, and we've already talked about side slopes and how the side slope factors into calculating the cross-sectional area. But how steep you can go with a side slope depends on what the channel is going to be made out of. If you're going to have a channel that is built out of rock, then you could actually have a vertical side slope. You can get away with the rectangular channel that we're always using in our calculations just because it's numerically easier. You wouldn't be able to get away with a rectangular channel if you're digging into sand, right? A sand channel isn't going to look like this sharp edge, but you could if you had concrete or if you had rock. So the side slopes that you select are governed by how cohesive the material is. The longitudinal slopes are just governed by the surrounding geography. If you're in a flat area, then your longitudinal slopes are going to be relatively mild, like that picture of Florida. Florida is not a very hilly state, and so their channels are very, very flat. Steep slopes may cause channel erosion, and so the way that can be prevented is with meandering. If you have a hill, then you can have the channel winding back and forth, and by winding back and forth, you have a more moderate slope than if you went straight down. Because remember that the slope is the change in elevation divided by the length. And so you reduce the slope here. This meandering path, the reason why it has a lower slope is because you're increasing L. You're taking a longer distance to get from point A to point B. In the straight line, you have a relatively small L, but in the meandering slope, you've got a big L. So it's just like skiing. If you've been skiing or snowboarding before, the way that you avoid going too fast is by going side to side down the hill. Here are some typical side slopes that can be tolerated in a variety of different materials. You'll notice that if you've got sandy materials, then maybe the best you can do is a 3-to-1 side slope, whereas with rock, you may be able to have a vertical side slope. And there's a variety of side slopes in between depending on what the material is that's being used. Okay, so freeboard and super elevation is that splashing that we talked about, and there's an empirical relationship that if you know basically how deep the flow is going to be, y, and you know the flow rate, then you can select a C value. This C value is just strictly empirical that you interpolate between given flow rates, and then you can calculate in meters what the required freeboard is. We won't work an example with this freeboard equation. It's not of primary importance. It's just sort of an empirical estimation of how much extra capacity you'd want to give so that when you're going around a bend, the water doesn't spill out the side of the channel. And here's the equation that allows you to calculate super elevation height. Super elevation is the difference between the lower end and the upper end. And so you can see this little black line here, the difference between the bottom end and the upper end. You could calculate based on the velocity of the flow, T, the top width of the channel, G is the gravitational constant, and then R is the radius of curvature. And so over here on the board, when I was drawing a curve that was like this, our radius of curvature is this. And so the tighter the turn, and if you had a turn that was of a larger radius, then that's going to lead to less superelevation. And it's down here in the denominator. So the larger the turn radius, the less the water is going to slosh around to the side as you're going around a bend. And this is a lot like when we were talking about Euler's equation and the effect that has in fluid mechanics. If you're accelerating a liquid, then the water will rise on one side of a container. Well, this is a centripetal acceleration when the water goes around a curve like this. And so this is actually, this equation is fundamental for estimating the difference in elevation due to going around a bend. So the question comes down to, should we line the channel or leave it unlined? Because the lined channel costs more money, but it does bring with it certain advantages. If you've got a concrete lined channel, then that's going to enable you to have higher velocities. And therefore, it reduces the cross-sectional area if you've got a higher velocity going through it. You know, if you wanted to use up as little land area as possible, then maybe you'll take the straight line path from A to B. You know, if water's going down the mountain in a straight line path, you're going to have to line the channel with concrete to try and make it more resistant to scour because the velocities are going to be very high. Another advantage of using a lined channel is that generally that decreases the amount of lost water due to seepage. So if water is considered a precious resource and you don't want to lose it, then a lined channel enables you to avoid that. On the other hand, the unlined channel is good if you're using like water as a waste. If you're trying to get rid of storm water, then an unlined channel is better from that perspective. To design a lined channel, then you first start off with selecting the material and the flow rate that has to be carried. Selecting the material is often just a function of talking to the material resource providers in the area, you know, the people who provide concrete, or it might be that you have access to a geosynthetic liner, like a plastic liner that could go on top of clay section. And then you find the end value for that material. The flow rate to be carried would be given to you by the hydrologist, saying, you know, what the flow rate coming out of a canyon where you're trying to convey the water from place to place, or it might be that you're conveying water to a water treatment plant, in which case the flow rate is maybe dictated by the demands of the flow by the water treatment plant. The end value is related to the material. The freeboard coefficient would be selected based on this interpolation and the calculation for how much extra capacity over and above where the water surface turns out for freeboard. Computing normal depth of flow from Manning's equation is how we find the depth. And then you check the velocity and the Froude number. And the reason why is that typically you want to avoid supercritical flow if you can, because it's prone to scour, and if you get supercritical flow at a certain section, then it's going to have to go through a hydraulic jump when it transitions to subcritical flow. So you want to avoid supercritical flow. Even though hydraulic jumps are fun to look at, they can be a little bit unpredictable and risky if you have one and you don't know exactly where the jump is going to set up, and you're not prepared for it. It can cause problems. The rule of thumb is that if you've got a non-reinforced lining, you want to have the flow rate under 2.1 meters per second. So non-reinforced would mean like if you have concrete, but it's not heavily armored concrete. But if you have a channel that is going to have really high velocities, you can have up to 5.5 meters per second if you've got a reinforced lining. All right, so here's an example that takes us through the process of designing a reinforced concrete trapezoidal channel. And there an extra copy of the notes? Got 15 minutes, and I want to leave you about 7 to do the teaching evaluations, so I think we'll be okay. Okay, we're going to design a line channel here to carry 2.4 cubic meters per second. So first of all, step 1, we're going to use concrete. And the end value of this concrete, let's just say we're going to pick in the middle of the typical values for its roughness. 0.015 would be a little bit more rough than the standard 0.013 that we sometimes select. We know that the flow rate to be carried is 2.4 cubic meters per second, and the channel slope is 0.005 in this example, so 0.5% slope. For step 2, estimate the roughness coefficient and the freeboard coefficient. Okay, so the n value we already said, n is 0.015, and the freeboard coefficient c, we know from the previous slide that a c value is 1.5 at a flow rate of 0.57 cubic meters per second, and it is 2.5 at 85 cubic meters per second. So basically what I'm going to do is a linear interpolation where I've got the flow rate Q on the horizontal axis, and it's ranging from 0.57 to 85. And then on the vertical axis, I've got C values ranging from 1.5 to 2.5. So I've got a curve there. And if I find the slope of that curve, the slope of it is 0.01184 per cubic meter per second. This is units of C for every increase in flow rate. Basically, going through that process, I can find that at the flow rate that we've got, at our 2.4 cubic meters per second, the C value I should select is 1.522. So not too far from the 1.5 that was associated with 0.57 cubic meters per second. To get up to 2.5, I'd have to have a much higher flow rate than I do. Normal depth. Using Manning's equation, we're going to assume that we're going to design it to be the best hydraulic section. So we're going to use the best parameters. And what that means is that the wetted perimeter is going to be 2√3 times the depth. The area is going to be √3 times y squared. B is going to be 2√3 divided by 3 times y. B is the channel bottom width. And then the side slope here is √3 divided by 3. So this is a trapezoidal channel that's actually fairly steep. The side slopes are steeper than 1 to 1. In this case, the side slopes are, I think it works out to about 0.577 to 1. So it's a relatively steep trapezoidal channel. So that if I put that into Manning's equation and solve for the flow rate, Q is the area divided by N, area divided by the wetted perimeter to the 2/3, and slope to the 1/2. So I've got 2.4 cubic meters per second, √3 times y squared for the area, put in the n value of 0.015, and then the ratio of the area to the wetted perimeter is √3 times y squared for the area, wetted perimeter to √3 times y, that's to the 2/3 power, and then the slope 0.005 to the 1/2 power. Okay, so solve for y, and we get the normal depth will be 0.7514 meters. And so now that we know what the depth would be, and you can get the channel width B, and you can find out what the wetted perimeter is going to be. And so under the design condition, the flow depth here would be 0.751 meters. And then the channel width, B, I can find that as B will be 0.868 meters because I just multiplied the depth I solved for by 2 root 3 divided by 3. And so that is 0.868 meters channel width. Okay, the flow velocity I can get just from the continuity equation, Q equals VA. So step 4, we want to check the velocity and see where we're at. In designing the channel, we want to know the velocity, so that's Q divided by the area. And we know from the beginning that our flow rate is 2.4 cubic meters per second. And the cross-sectional area is going to be root 3 times y squared. That is root 3 times 0.7514 meters squared. So the velocity of flow is going to be 2.45 meters per second. And that's good. We know that it's going to be acceptable against, there's not going to be any sediment that will form here. You'll notice the velocity above 0.9 prevents sediment, and velocity above 0.75 prevents vegetative growth. So, that's okay. No sedimentation. No vegetative growth. Like weeds and cattails, that sort of thing. You'd want to avoid those from growing in your concrete channel, in the cracks and the seams. Sedimentation forms when the silt that's being just suspended naturally in water, sand and silt, if the water's moving slowly enough, then there isn't enough vigorous mixing to keep those particles suspended. And so that then the water would, the channel would begin to get filled up with sedimentation. So we're good with the flow being 2.45 meters per second. The last thing is we're going to see how much extra freeboard elevation we'd want to provide for. And in this case, the freeboard would be using this empirical expression 0.55 times the square root of 1.522. That was our C value, times the known depth of 0.7514 meters. We'd want to have an extra 0.588 meters over and above where the flow depth is going to be. So if the flow depth is going to be 0.751, then we want to make sure that this extra height above where the water surface is expected to be, here, that depth is going to be 0.588 meters. All right. Let's leave that example here because I just want to show you one other concept and then we will call it a day. We'll call it a semester. Well, the final exam, we'll call it a semester. We'll call it a class. In Unlined Channel, you have to go through and compare the shear stress that's applied to the channel surface with the cohesive strength of the soil. And so if you don't have concrete there, the question is if water is flowing over earth, is the shear stress of the water going to disrupt the earth, or is the earth holding together with enough strength that it won't be scoured? And what this graph shows you is for the particle size in inches and the angularity of the soil, what a typical angle of response is. An angle of response is if you're starting to make a stack of some material, what the angle with the horizontal would be. And so you can calculate the shear stress on the bottom of the channel by the slope of the energy grade line, the hydraulic radius, and the unit weight of the fluid that is being transported in the channel. And so what you would do in an analysis like this, if you've got an unlined channel, is you would use this expression to calculate the shear stress, and then you'd go through a soil analysis and try and find out what's the cohesive strength of the soil. So in the case of the hydraulic engineer would just get an answer from the geotechnical engineers, what's the strength of the soil, the shear stress strength of the soil. The design procedure has some similarities to what we do when we have a lined channel, except that we're going to want to have much lower velocities than we would in the case of a lined channel, because the concrete was able to resist a lot more scour than an unlined channel will. Okay, so that is where we're going to leave it for now. What I'd like you to do, if you haven't already filled out the evaluations, grab one of the tablets and go to MyMU. That's where you can get the course evaluations. I think last time I looked, 7 people had done the course evaluations. I can't see them yet. I just get an email every couple of days that tells me how many students have finished them. I'd be especially interested in your feedback if you have anything else to say on the project. If you didn't get a chance to share your opinion on the project, I'd be interested to hear that. And you know, any suggestions on how the course can be improved, feel free to add those to the feedback. Otherwise, that's it for today. I'll see you at the final exam on Tuesday the 6th, and I'll send you an email when I get the assignments back from the grader.